Climbing up a sheer cliff. Why does it have to be 90 degrees? Because that way we're all on the y-axis. If it had some angle, we'd have to do vectors, and we don't know how to do that yet. So, well, the drawing's a little bit funky. So we've got our banana clutched in our teeth, and you drop it. Whoops. So the banana has an initial velocity of 1.3 meters per second upward, because the banana is moving with you. So what we want to know is, what is the velocity of the banana after delta t equals 2.5 seconds. So we know acceleration is negative 9.81 meters per second squared. So we've got VI, A, delta t, and we would like to have VF. Well, that gives us VF equals VI plus A delta t. And you don't even have to rearrange anything. You plug it in. Your raw answer is negative 23.225 meters per second. And with sig figs, your final velocity is negative 23 meters per second. So straightforward and simple enough. Okay, so this is one of the classic. We want to know maximum height on a thrown-up object. And so VI is positive 15.9 meters per second. Acceleration is gravity, so negative 9.81 meters per second squared. And we know VF because we're talking about the top of flight, so VF is going to be 0. And what we would like is delta Y. So delta Y is what we want. This is a nice place to use VF squared equals VI squared plus 2A delta Y. So we rearrange to solve for delta Y. Okay, so if we rearrange it, we get VF squared minus VI squared divided by 2 times acceleration gives us delta Y. Well, that gives us 0 squared minus 15.9 meters per second squared over 2 times negative 9.81 meters per second squared equals delta Y. We get a delta Y, it's 12.8853.211 meters is our delta Y. Now, the thing that you have to remember is that the max height is not delta Y here. So if this was thrown and it left ground level at that velocity, then max height and delta Y would be the same. Max height is delta Y plus that 1.5 meters because it left the ground 1.5 meters off the ground. So delta Y and max height are not the same, and that's a really common sort of trap that I set. It's also a really common situation. When you throw something up in the air, you don't typically project it from ground level. You have some wind up, and those of you who threw or fired objects upward know that. So we get a max height with sig figs of 14.4 meters, so your friend has ample opportunities to catch it. Actually, they have 2 opportunities to catch it. They can catch it going up, and they can catch it coming back down, because it's going to go up over their head and drop back down. So yes, they can catch it. The 1.5, that's the entire height that it travels to. The 8.75 is there just for comparison, so you don't do anything with that number. The other trick in problems like that is that maybe everything else has 2 sig figs, but the number you're comparing it to has 3. If it didn't go into your calculations, you shouldn't use it for sig figs. You only use the numbers that you used to calculate in your sig figs. Okay, so here we're asked if that ball either doesn't reach them or if they don't catch it, how long is it in the air total before it crashes back to the earth? So we have VI, we have A, we have delta Y. What's delta Y in this problem? Negative 1.5, because it started off 1.5 meters above the ground, and so its initial position and its final position have a difference of 1.5 meters. So it got nothing to do with how high it goes. We don't care how high it goes at this point. So if we want to solve for delta t, we've got an easy way to do this with substitution. We can use VF equals VI plus A delta t, solve for delta t, VF minus VI divided by A equals delta t. So we've got this. Of course, we don't have VF. And one trap you could fall into was saying, oh, well, VF is 0, not for the whole flight. So VF is only 0 at that top of flight moment. To solve for VF, we have to create, or rather to create an expression for VF, we want to use this, 2a delta y. So VF equals the square root of VI squared plus 2a delta y. And we're going to plug this entire thing into that problem. So what we get is square root of VI squared plus 2a delta y minus VI all over acceleration equals delta t. And at that point, you're just plugging stuff in. The things to be careful about are making sure that you get the right delta y. VI is easy, A is easy. So we end up with a raw answer. Here's the other tricky part. Now, I didn't write down my intermediate numbers, but if you write down the intermediate number for this final velocity, it's plus or negative. It's plus or minus. It's positive or negative. We don't know because you took a square root. If you use the positive of that and you subtract your initial velocity, you get a positive number, which divided by acceleration gives you a negative time. And whenever that happens, that should be a red flag. And you go, ah, there's a problem. Because the magnitude of the difference between final and initial is different if it's a positive final or a negative final. So you had to make sure that you did that. The raw answer that you should get is 3.33333. Repeating is delta t. We can have 3 sig figs, so that becomes 3.33 seconds is delta t. That's the elegant way to do it. One other way to do it that people sometimes do, I don't remember if anybody did or not, is to figure out the amount of time it takes to get up to the top of flight. You know, to the amount of time it takes to get to the point where VF is 0, and then figure out that height and figure out how long it would take to fall. There are so many potential places to screw that up because you're counting on multiple numbers that you've calculated. So I really advise against that. Do the elegant, straight through kind of solve. Number 4, you're on some alien world, so we don't know what acceleration is here. Here on Earth, it's negative 9.81 meters per second squared. On an alien planet, depending on the alien planet size, it could be more or less. We have no idea. So you're testing this scientifically by dropping your thermos, and when it falls, you seize your opportunity and time it. So it takes a delta t of 4.75 seconds, and you happen to know that the cliff, the delta y, is 58.5 meters, giving your object a delta y of negative 58.5. What was VI? 0. Yeah, because you dropped it. So we've got VI, delta y, and t. We want acceleration. This seems like a great place to bust out the old delta y equals VI delta t plus 1/2 a delta t squared. Because VI is 0, that just goes away because that'll multiply into 0. And we can rearrange from there. So 2 delta y divided by a. Oh, wait a second. What did I do? I'm solving for t. Silly, silly Moser. 2 delta y divided by delta t squared equals a. So we have 2 times, our raw answer is negative 5.185595, etc. meters per second squared is our acceleration on this planet. It's sig figs to negative 5.19 meters per second squared is the acceleration on this planet. Questions? Okay, so we're doing, this is 5B on page 64. If somebody does not catch the apple when it's thrown up to the treehouse, how long is it in the air? This is very much like the problem that we just did on the quiz. So we have a VI, we have a delta Y. In this case it was thrown upwards from 1.3 meters. So delta Y is negative 1.3 meters. And we have acceleration, of course, negative 9.81 meters per second squared. And we want delta T. So we can do, oh, where'd my note card go? Well, actually, I'm just going to copy it from the last one. So we can do VF equals VI plus A delta T, and rearrange to solve for delta T. So, oops, VF minus VI divided by A equals delta T, but we don't have VF. So we're going to create an expression for VF using VF squared equals VI squared plus 2A delta Y, because those are all things we do have. So we have VF equals square root of VI squared plus 2A delta Y. And we can take that whole thing and plug it right in for VF. So we end up with VI squared plus 2A delta Y minus VI over acceleration equals delta T. Okay. Does that seem reasonable? Okay, so for number 40 from the chapter review, we're told that we have this 15-meter tall building, and we've got a ball being thrown upward from the ground, so they're specifying that it's at ground level with an initial speed that's given and one that's dropped from rest, and what we want to know is at what time will they be at the same height. So here's what we know. We know that the change in position of the thrown ball minus the change in position of the dropped ball equals 15. So delta Y throw minus delta Y drop is going to equal 15.0 meters. And the way to sort of logic this through for yourself, because I always struggle with, well, which one do I need to subtract? If you imagine that the thrown ball has risen 10 meters in the air, whoops. So if this number is positive 10 meters, and that the dropped ball has fallen 5 meters, so minus negative 5 meters, that does equal 15. That's true. So because the change in position on the drop ball is going to be negative, that's how to handle it. So then we just need to create an expression for each of those and work out the details. Okay, so we've got expressions for both the thrown and the dropped ball. So far, so good? Ja oder nicht? Okay. Here's something really important to remember when you're doing these kind of problems, and we do a lot of these kind of problems in Chapter 3. So here, you have two different VIs to keep track of. You have the VI of the dropped ball and the VI of the thrown ball. So I use a little subscript. So this is the initial velocity of the thrown ball times delta t plus 1/2 a delta t squared. Now, their accelerations are going to be the same. Their times are going to be the same. So the only thing here that varies from one object to the other is their initial velocities, and those are tremendously different. So that minus VI of the dropped ball times delta t plus 1/2 a delta t squared. Okay, well, two things happen really quickly. Number one, this goes away because VI of the dropped ball was what? 0. It had no initial velocity. So that was 0. So now, so a couple things happen. So we now have VI thrown times delta t plus the expression 1/2 a delta t squared minus 1/2 a delta t squared. Guess what happens? Those go away. You're subtracting the same thing. So this whole thing, of course, is equal to 15.0 meters. So now you have The initial velocity of the thrown object times delta t equals 15.0 meters. Solvable? Other questions? Okay, so that's it, and tomorrow homework is due. We will grade and go over homework, and then test on Wednesday, multiple choice, and work out over all of Chapter 2.